Hi, everyone. My name is Brandon Rodriguez. Thank you so much for joining us today. I work at NASA's Jet Propulsion Laboratory in Pasadena, California, in the Education Department. And today we have yet another one of our really exciting videos looking at what's next for space science. If you've joined us over the last few months, you've noticed we've talked a lot about Mars, Mars being our neighbor, the target of so many really exciting missions that are still underway. And we had a lot of really cool activities leading up to the Perseverance landing and discussed a little bit about the first test flight of the Ingenuity helicopter. All of these things are really, really fascinating, but um, I'm personally really delighted to spend some time talking today about the rest of our solar system. There's so many exciting things taking place and so many other destinations for us to explore. So with that in mind, we're joined today by Cynthia Phillips, who's a planetary geologist, and she's going to talk to us about the place that I think is the most exciting in our solar system, which is the moon Europa. So today we'll hear a little bit from her, and then we'll answer some of the questions that you have for us. So if you're registered online, submit your questions, and we'll make sure to answer them here live today. At the end of that, we'll discuss a little bit about how this ties into the work we do at the Education Office, and how you can take this really exciting research to your classrooms, to your students, to your children at home. So with that, I want to get right to it. Let's turn it over to Cynthia and hear a little bit about some of the cool watery worlds for us to explore in our solar system. Cynthia, please.
Hi, everyone. So we can bring up slide number 2. So my name is Cynthia Phillips, and I'm a planetary geologist here at JPL. And a planetary geologist means that I like studying planets, and I like studying what the surfaces of planets look like. And one of my favorite places to study actually isn't a planet, it's a moon. It's a moon of Jupiter, and this moon is called Europa. And so this is a picture of Europa. And so while Europa is about the same size as Earth's moon, it looks completely different. Instead of the surface being covered with old craters, with holes, with ancient lava flows, instead Europa's surface is covered with ice. And that ice has cracks and ridges and places where it's been broken up. And it makes Europa a really amazing looking place. But scientists think that it's even more exciting what's going on underneath all that ice. So Europa, I'll tell you today how it's one of the best places to look for life in the solar system beyond our Earth. And we think that Europa has all of what we call the planetary ingredients for life. And these ingredients include liquid water. They include the right essential elements. So those are things that life is made of, like carbon, hydrogen, nitrogen, oxygen, phosphorus. Those are things that we call the building blocks of life. And we also think that Europa has enough energy. It has an energy source that could help life form and survive and thrive there. And it also has stability. What that means is that we think that Europa has had these conditions that could support life for billions of years. So today I'll tell you a little bit more about why I think Europa has these planetary ingredients for life, why Europa is just so amazing looking, why it's better than Mars, because come on, it is kind of better than Mars, I think, even if it doesn't have a helicopter yet. And I'll also tell you how we're going to explore Europa in the future with some of our spacecraft missions. So on slide number 3, you can see that you can see Jupiter. And so Jupiter is the biggest planet in the solar system. It's actually so big, it has more mass than all the other planets and satellites in the solar system combined. It's this gigantic planet. And so if you see the little kind of doodles at the top of this that look like little stars that somebody drew with a crayon, that's what we used to think Jupiter and its 4 big satellites looked like. A guy named Galileo, back hundreds of years ago, was one of the first people to look at the stars with a telescope. And when he looked at Jupiter, he saw that there were these little bright stars right next to it. And he was a really smart guy, and he figured out these weren't just stars, these were actually moons that were orbiting around Jupiter. And this was a huge deal because this was one of the first times that humans had realized that there's things in the universe, there's things in our solar system that don't rotate around the Earth. And in fact, Galileo was one of the first people who figured out that the planets all orbit around the sun, that Earth and Jupiter and everything else orbit around the sun, and that some of these planets had things orbiting around them. And so because of this amazing discovery, we call these the Galilean satellites. And these are the 4 big satellites of Jupiter. We have Io, which is the closest one in. And Io, sometimes we call it the pizza planet because it kind of looks like a pizza. It's kind of orange. It has like tomato sauce. Then it has some cheese, some nice yellow and white cheese on it. And I don't know, those black things, maybe they're anchovies or olives or something. I don't like those, but some people do. And actually what's going on in Io is those are volcanoes. Those are lava flows that are spewing material out onto the surface. And Io is actually the most volcanically active body in our whole solar system. And so next to Io, you see Europa. And Europa's surface is covered with ice. It has cracks and ridges and broken up places. The parts that look kind of bluish white in this picture are pretty pure ice. And the parts that are more kind of red and brown, those are places where the ice has other material mixed in with it. And then we have Ganymede and Callisto, and these are 2 bigger moons. And basically what's going on there is that Ganymede has some kind of old craters. It looks a little bit like Earth's moon. And then it has some places where you can see some of these kind of old cracks and bands on the surface. And then when you look at Callisto, it's just covered with craters. It's a whole ball that's been smashed into by asteroids and comets and meteors over and over again for billions of years. So there's not that much going on in Callisto. So what's really interesting here is that the closer you are to Jupiter, so these pictures show the moons, they're in order, so it shows their sizes, so their relative sizes are correct, and their order of distance from Jupiter is correct. So Io is the closest, and Callisto is the furthest. But there's a lot of space between them, so this doesn't show the distances correctly in this picture. But what we can see is that Io is the closest to Jupiter, and it's the most active. It has the most energy that it's giving off. And Callisto is the furthest away, and there's the least going on there. So that helps to give scientists a clue that something interesting could be going on. We know that something interesting is going on in Io with all those volcanoes, but it helps scientists think that, maybe under that ice on Europa, there's something interesting going on there too. And so on slide number 3, you can see what Europa's surface looks like in a little bit more detail. So slide number 4 is basically showing that we have the surface of Europa, and on the surface, there are ridged plains. Those are places where they look smooth, but when you zoom in, see all there's cracks and these ridges, these weird looking places. You can see there's what's called chaos terrain. Those are places that almost look like icebergs where the surface has been broken up into pieces and moved around. There were a few craters on Europa, but not very many. And then there's things that we call lenticulae, and that's just a fancy way of saying little spots on the surface. That means freckles in Latin. So these little like dark spots in round places. We're not really sure how those are made. And so if we take a look at slide number 5, what we can see is the inside of Europa, Europa's interior. So we know there's that ice shell at the surface, and underneath that ice shell, we're pretty sure there's an ocean. And this ocean, it's made of liquid water, just like Earth's oceans, and it's huge. We think there's actually more water in Europa's ocean than in all of Earth's oceans combined. But it's not water all the way down. Under that water, there's a layer of rock and then a layer of metal in the core. And this is kind of like the Earth. So basically, Europa is kind of like an Earth with a metal core in the middle, rocks above that, water above that, except that instead of on the Earth, we have an atmosphere of air. On Europa, there's a layer of ice. So the surface is all frozen. And it's that ice layer that helps keep the water layer safe and liquid underneath it. And so how do we think that water layer stays there? How do we think that Europa is so far away from the sun? It's really cold out there. And so you'd think, well, there wouldn't be any liquid. It would all just be frozen solid ice. But what's going on is something called tides. So tides are what makes Earth's ocean move up and down. If you've ever been to the beach, you know that sometimes it's high tide when the beach is really small, and then sometimes it's low tide when the ocean's kind of gone out and you have a lot more room to run around on the beach. So that's actually caused by the gravity of Earth's moon tugging on Earth's oceans. And the same thing happens on Europa, where the gravity of Jupiter tugs on the whole body of Europa, but especially on its oceans. And so you can see in the little animation that Europa is getting stretched and pulled as it goes around Jupiter by its strong gravity. Sometimes the surface gets stretched out, and then sometimes it goes back down. And that's because the distance between Europa and Jupiter changes over the course of a couple days as Europa goes around Jupiter. And so the surface gets stretched and pulled, and that heats it up. And we think there's actually enough heat to keep Europa's ocean liquid. So this is a really cool discovery that we found. And if we go ahead onto slide number 6, you can see that there's a lot of water on Europa. So on Earth, if we took all of Earth's water from the oceans and we put it just into a ball, it would have the size in this picture here. And you can see that for Europa, there actually could be twice as much water from all of Earth's oceans. And then we look at Mars. You know, Mars is cool. It has a bunch of rovers driving around on it. Does it have any water? Not today, it doesn't. We think maybe back way in the past, you know, a couple billion years ago, Mars could have had water, could have had an ocean on the surface, just like Earth. But today, Mars is a giant desert. It's cold and it's dry, and there's only a very thin atmosphere. And there's some ice frozen in the poles of Mars. But as far as we know, there isn't any liquid water, certainly not on the surface, maybe deep underground, but we haven't found it. So that's why when we start thinking about places for life in the solar system, thinking about life on Europa is really exciting because there's water. There's an ocean on Europa today. And so if there's an ocean, there could be life. There could be things living in that ocean. And that's one of the reasons why people like me are so excited about Europa. So if we go ahead to slide number 7. So we talked about ingredients for life. And so we need water. And so there's more water than all of Earth's oceans. So we checked the box for water. So there's the right essential elements. So these chemicals that I talked about, some of those could have been there when Europa was formed, and some could have been brought to Europa by comets and pieces of asteroids that crashed into the surface. We think there's chemical energy. So there could be what's called hydrothermal systems. And so the video on this slide here, this is not Europa, okay? This is the bottom of Earth's ocean. I wish this was a video from Europa, but we don't have videos like this from Europa yet, maybe someday. But what's going on in this video is we're looking at a hydrothermal system, a black smoker at the bottom of Earth's ocean, where there's hot material that's coming up from a crack in the ocean floor. And what happens is that the water at the bottom of Earth's ocean goes and it mixes around. It mixes with this hot lava, this hot material, and it creates all of these interesting nutrients, and it's a great place for life. And so when we look for life on Earth, we thought, well, the bottoms of Earth's oceans, that there's not going to be anything living down there. It's so far away from the sun. But then when we went down there in submarines and we looked, we found all this life. And so Europa, remember the bottom of the ocean, it's a layer of rock. So we think there could be hydrothermal systems in Europa's ocean as well. And so those could be great places for life to survive and thrive. And so again, we also have this stability. We think that Europa's ocean has been simmering for 4 billion years, for almost the whole age of the solar system. We think this ocean formed right when Europa formed, really. And so that's a lot of time. And we think maybe that's enough time for life to form there. So if we go ahead to slide number 8, this is showing you some of the other features. So again, we haven't seen what Europa's ocean looks like. We only know it's there through indirect evidence. but we have seen the surface of Europa. And so this is just showing you a little zoom on one of those ridges on the surface of Europa. There's these cracks, and we think these cracks kind of open and close, and they sort of squeeze up material, and that's how they build up into these ridges on the surface that we're seeing. And you can see that they're huge, right? So they're a couple hundred meters tall. They're maybe about 2 kilometers wide, but they go on for thousands of kilometers in both directions across the surface. And if you look at what's behind this big ridge we're looking at, there's a whole bunch of little ridges. So it's kind of like a ball of yarn that's been all wrapped around, and that's kind of what the surface of Europa looks like. And so if we go on to slide number 9, there's also places where instead of building up a ridge on the surface actually kind of spread apart, and it made these big smooth bands. They kind of look like alien superhighways that you could drive to work on. But, there's no cars there. There's no aliens there that we've found, but we have these amazing smooth kind of band-like features on the surface. And then if we go ahead to the next slide, slide number 10, where we have chaos features. This is what we call kind of the icebergs on Europa's surface. And so these are places where, see, there's all these ridges, and then the surface is actually broken up into blocks. And those blocks have rotated, they've translated, they've tipped, and then it's like they froze into new positions on the surface. And so while these are a lot bigger than any icebergs we have on Earth here, we think that maybe they're made with a similar kind of process where liquid or warm material got close enough to the surface to break up this surface layer and let it move around a bit. And so, and then what we think might be going on underneath this chaos, on slide number 11, we can see that if the surface is kind of broken up, this is another artist's illustration on the left here, where there's like a lake that's inside of the ice layer. So there's this ocean underneath, there's the ice layer on top, but there could be places inside the ice layer where there's actually liquid water, the little melt zones in the ice. And we think maybe these are under some of these chaos regions. Maybe that's how these sort of iceberg-like features got to move around on the surface. So all of this is what scientists think could be going on, but we don't know for sure yet. And so if we go on to slide number 12, one of the things we've been working on here at JPL is a mission called the Europa Clipper mission. And Europa Clipper is a spacecraft that will go and visit Europa. It'll be in orbit around Jupiter, actually, but it'll have multiple close flybys of Europa. And the goal of Europa Clipper is to explore the habitability of Europa. And so what habitability means is, are there places at Europa that could support life? So it's hard to find life. And so looking for habitability is kind of one of our first steps that we need to do when we're thinking about how we would look for life. And so what Europa Clipper will do is it'll study the ice shell and ocean of Europa. It'll study the composition of the surface. It'll study the geologic features, and it'll look for any activity that's going on. We've maybe seen signs that there could be plumes ejecting material off of Europa's surface, but we're not sure yet. And it'll also perform what's called reconnaissance, and that means it'll take pictures that will help a future mission actually land on Europa. And I'll show you more information about that toward the end of this. So if we go on to slide number 13, there's 2 kinds of instruments that are on Europa Clipper. And so the first time set shows the remote sensing instruments. So these are instruments that will observe Europa from a distance. There's an ultraviolet instrument, there's a camera that looks in visible wavelengths, there's one that looks in near infrared wavelengths, there's one that can look for hot spots, and there's even a radar instrument that could try to look through the ice shell. And then there's what we call the in situ instruments. And so these aren't going to actually land on Europa, but what they do is they measure material that's thrown off of Europa. So there's what's called a mass spectrometer and a dust analyzer. These will tell us the chemical properties of the dust and the gas that's thrown off of Europa's surface into space. It's kind of like the spacecraft can stick out its tongue and taste this material and try to figure out what it's made of. Is it salty? Is it sweet? What is it, is it yummy? Is it gross? That's one of the things the spacecraft can do, but in much more scientific terms. And then there's also a magnetometer and a plasma instrument that will study the magnetic field of Europa. And so if we go on to slide number 14, here's a picture of what the Europa Clipper spacecraft might look like. And then on the right, there's a little animation that basically is showing a little bit about how Europa Clipper is going to get to Europa. And so you can see how it's going in circles around Jupiter. As we're zooming in, it's getting closer and closer. This is when we first get to Jupiter. And then when we get close enough, we're going to start doing flybys that go past Europa. And so basically on each orbit, there's a lot of radiation at Jupiter. And so we don't want to spend too much time right at Europa. So what we do is we go in, do a close flyby of Europa. It's kind of like we hold our breath, we get in really close, we take all our pictures and observations, and then we zoom out of there. And then we can kind of take a deep breath and we can play back all of our data back to Earth, and we can get new instructions for what's going to go on the next orbit. And you do this again and again, and that's what all these circles are. This is what all the orbits would look like as you build them up over the course of a couple years in orbit around Jupiter. And so on the next slide, slide number 15, we can see that by doing this, we can build up what's called a global web of flybys. So each flyby on the closest approach, it goes by a different part of Europa. And so what we can see is that we'll get to see underneath us on the spacecraft, we'll get to see all sorts of different features and all sorts of different places on Europa by doing about 40 or 50 flybys, or maybe even more if we get to have an extended mission on Europa Clipper. So the next slide, slide number 16, is showing us what an artist's conception of a plume fly-through might look like. And so again, this is a video, so this is an animation. We haven't actually been there yet, but if there are plumes that are going on that are erupting from Europa's surface, then the Europa Clipper spacecraft could actually fly through one of these plumes, and it could sample the material. So remember the instruments that are kind of sticking out their tongue and measuring the composition? Those will work even if there's no plume at all, even if all we have is just a little tiny bit of atmosphere on Europa. But if there is a plume, they're going to get a whole mouthful of tasty, tasty stuff, and they'll work even better. They'll be able to tell us the composition of so many more kinds of materials. So I think we're all hoping that there's plumes on Europa, but we don't know for sure if there are, and we're not going to know until they get there. And so on the next slide, slide number 17, this is telling us about the follow-up mission. So Europa Clipper, the mission I talked about, we're currently working on building it here at JPL. It's going to launch in a couple years. It'll take about 5 or 6 years to get to Europa. And so we're going to be seeing pictures from that spacecraft. You know, you'll have to be patient, but we're going to get to see them. So what a lot of people really want to do, though, is actually land on the surface of Europa. You know, it's one thing to see it from space, but it's another thing to actually see, like, what would it look like to be on the surface? And so another mission that we're working on is called the Europa Lander Mission Concept. So this is not an approved mission yet. We're not building it yet. We're just studying how we would build something that could land on Europa. And here's what the spacecraft maybe could look like. And so if we go on to slide number 18, the science goals for actually landing on Europa would be search for evidence of biosignatures on Europa. So a biosignature is a sign of life. So if you remember that Europa Clipper was going to be studying the habitability of Europa. So the habitability, it means, are there places on Europa where we think life could live? Once you actually land on the surface with something like Europa Lander, you can look for evidence that life is or was there. So a biosignature, it could be, you know, a fish on the surface, but we don't think there's really any fish going to be on Europa, especially not on the surface. We're talking like little microscopic life forms, most likely. And so maybe we could find evidence of those by landing on the surface and sampling the surface. And so Europa Lander would also be able to study the habitability of Europa, and it would also help to characterize both the surface and the subsurface of Europa. And on slide number 19, you can see here's what the Europa Lander mission concept would look like. So the idea is that you launch from Earth, just like with Europa Clipper. You have a big spacecraft with solar panels. You get out to Europa and you land on the surface, and it would actually use a sky crane crazily enough, kind of like how we landed the most recent Mars rover, Perseverance, where you have kind of a hovering rocket thing and you lower the lander on these long these long cables, and then it gently touches down on the surface. And it turns out that actually works pretty well in Europa too. And so that's how we're thinking we would land this. And so this is what the Europa Lander spacecraft on slide number 20, here's what it would look like on the surface. And so the idea is that you land on the surface and you would actually sample some of the material. And if we go on to slide 21, here's a video that kind of shows what this whole mission concept would look like. So the idea is that you arrive at Jupiter and your lander, it's inside a spacecraft like this. So this kind of looks like Europa Clipper, except see that there's a little circle thing with a square inside it. That square is part of the lander. So the lander is carried all the way to Jupiter on this carrier spacecraft. So we get to Europa finally. And then once we get there, we don't need the whole spacecraft that can fly in space anymore because we're going to land. And so here comes the lander. It comes out of the spacecraft and it's kept safe in what's called a biobarrier. And this is something that basically makes sure that everything stays super clean so that there's no contamination. We want to make sure we don't bring any hitchhiking life from Earth along with us, because when we land on Europa, if we find life there, we want to make sure that that life is actually Europa life, that isn't life that we brought with us by mistake from Earth. So here's the spacecraft. And so one interesting thing about Europa is that because there's no atmosphere, you can't use a parachute. So if any of you watched the recent Mars landing, if you watch some videos of it or some of the real pictures, the amazing pictures that it took, remember it had that giant parachute on it. But on Europa, we can't use a parachute. So see, there was a little rocket that brought it down close to the surface. And now here's the carrier stage. So this is the sky crane now. So it has rockets and it's on a tether and it has some landing legs. This isn't a rover. This would just stay still in one place and there. So it lands on the surface and the legs kind of bend and they adjust to the surface. And that's because we don't know how bumpy the surface is going to be. We'll do our best to find a place using a radar and other instruments on the way down to find a place that's nice and flat and safe to land. But just in case, these adjustable stabilizer legs can help to hold the spacecraft in case one of the legs ends up on a chunk of ice or something. So the spacecraft would land. It has an antenna and it also has a robotic arm. And so the arm would be able to dig below the surface with some kind of a scoop or a saw. We don't want to sample material that's just from the very top of the surface because that's been fried by radiation. And so instead, we'll use a saw or a scoop or something to dig down below the surface and to make a little trench. And then we'll pick up some of that material from below the surface and we'll bring that material on board the spacecraft. And that's where all of our chemical instruments are. So here, rather than the spacecraft sticking out its tongue like Europa Clipper is going to do as it flies past, here we're actually bringing this whole scoop into the mouth, right? So we're bringing this scoop of material on board the spacecraft. And then the instruments that are inside the spacecraft will be able to study it and they'll be able to look for signs of life. And we'll have some cameras and other instruments too that will help to tell us what Europa's surface looks like. So this is a mission that we're dreaming about doing that I think would be really amazing. I hope that I've told you why I think Europa is such an amazing place. Why, in my opinion, it's a little bit more interesting than Mars, but Mars is pretty cool too. So can't say anything bad about Mars. But Europa has this ocean that's there today. And we're studying it with the Europa's Clipper spacecraft that we're building right now. And maybe in the future, we can actually build a mission like Europa Lander that could land on the surface and directly look for signs of life.
Awesome. Yeah, thank you so much. I think this is just so thrilling, right? To imagine a place, and I'm with you, right? Mars is fascinating. But when we think about where life could be today, it's in these places like Europa. Something you mentioned, I was kind of hoping you could just expand on. You mentioned at the very beginning that Europa had the right ingredients for life. And you mentioned, had the right elements and the right energy. And I thought that was really important to spell out because for so long, we've talked about how um, if we're looking for life, we're looking in the habitable zone, the Goldilocks zone, the right distance from the sun, which Mars is, but Europa is not. And can you maybe expand a little bit on how it is that we even look for places where there could be life now?
Yeah, that's right. And that's really been one of the exciting things that happened in the last decade or two is that we used to have an idea of the habitable zone, like you said, where that's the distance from the sun where liquid water can exist on the surface of a planet. And so that means that Venus is too close to the sun, it's too hot. And then Mars, it's a little bit too far from the sun. So today, Mars is too cold. Water can't exist there, but Earth is just right. It's right in the middle. Liquid is stable at the surface. It's full of life. And so that used to be how we thought about looking for life in our solar system and also in other solar systems. And one of the really cool things that we've realized more recently is that we need to expand our whole idea of what a habitable zone is, because there could be moons orbiting giant planets like Europa, but in other solar systems as well. And those moons could have other sources of heating. So on the Earth, most of our energy comes from the sun. But out at Jupiter, the sun is 5 times further away, and that means there's 25 times less sunlight. So if you were on Europa and you were looking at the sun, it wouldn't be this giant blinding ball of fire in the sky. It would just be kind of a bright star. You could still see the sun, but it wouldn't be anywhere near as spectacular as it is here on Earth. And so the sun is just not a source of very much energy when you're out at Europa. And so instead, there's this other heat source, which is this tidal heating by the gravity of Jupiter. And we think that that sort of heating could take place. There could be many other ocean worlds in our own solar system. There's this little moon of Saturn called Enceladus that does have these geysers of material being spewed out into space. And so maybe there could be life there. And maybe when we start looking at solar systems that are around other stars, a lot of those solar systems seem to have big Jupiter-like planets that could have moons around them. And so what that tells us is that, yeah, we need to think about a much broader range of places where maybe life could exist.
Yeah, moons that we, of course, can't even detect, right? As we're very lucky to even be able to see exoplanets at all.
Right.
But to be able to see moons around those exoplanets is far more difficult. So yes, who knows what's out there? So we have a bunch of submitted questions, and I think the most important ones to address first are, you mentioned Enceladus that does have these giant plumes, and we're able to do a little bit more advanced detection on what's inside those plumes. How are we doing that for Europa? So how do we know, even just those fundamentals that you mentioned, that Europa is made of ice water and that there is liquid water underneath?
That's a really great question. And actually, it comes from a whole bunch of what we call indirect or kind of circumstantial evidence from various telescopes and spacecraft, especially a spacecraft called the Galileo spacecraft, named after the guy who, discovered the moons of Jupiter. So the Galileo spacecraft was at Jupiter in the late 1990s, and it took a whole bunch of pictures, but it also had a whole bunch of other instruments. And so as we started putting together all of the scientific information from all those instruments, we built up a picture that said, hey, there's got to be an ocean there. So for example, we got gravity measurements, and those gravity measurements said there has to be a layer of something with the density of either ice or water that's a layer about 100 kilometers thick at the surface. And so the gravity measurements, though, they couldn't tell us how much of that was solid ice and how much was liquid water, because the densities of those two are so similar. And then we looked at the pictures, like the one of the iceberg regions that I showed you. And so there, the geologists were saying, well, it really looks like the surface has been broken up by something underneath. And it turned out that it was actually the magnetic field results that gave us the most definitive evidence for an ocean. And it's a little bit of a complicated story, but basically when you have a conductor, so that's a material that can conduct electricity that moves through a magnetic field, then you can generate a signal, a very particular signal from that conducting layer. And so it turns out that Jupiter has a really strong magnetic field. Europa doesn't have its own magnetic field. And so when scientists on the magnetometer on Galileo they were looking at Europa and they were surprised to see that there was this signal coming from Europa. And they figured it out, and they basically said that the only thing that could be giving off this signal is if there's a global conducting layer on Europa that's moving through Jupiter's magnetic field, it would be giving off this signal that they got. It's called an induced field. And it turns out that salt water is a really good conductor. So it was actually the magnetic field results, the magnetometer results, that were the most definitive evidence of an ocean below Europa's surface when you combine that with everything else. So we're really excited to get to go back with the Europa Clipper spacecraft and confirm the presence of an ocean. So exactly, we still don't know for sure how thick that ice layer is at the top and how thick the ocean layer is underneath. We just know that the whole layer itself is about 100 kilometers thick.
Gotcha. Yeah, and of course, like I know that one of the more exciting pending results from something like Europa Clipper would be to get a feel for some of those depth measurements. Is it from those original gravity and density measurements that we at least have an idea of the thickness of each layer? How is it that we know that there's a rocky core underneath, for example?
Right, and that's something we can also do with these gravity measurements. What these gravity measurements do is they don't just tell us the gravity of Europa as a whole. What you do is you look at how Europa Clipper or any spacecraft, as it flies past Europa, it gets tugged on by Europa's gravity. And if you build up these tugs over multiple orbits, you're able to start figuring out, okay, it's not just one big ball of something tugging on me, but it's actually layers. And so they're able, it's really cool. And it's a really cool reason to learn a lot of math, because there's a lot of math required to do this. But they use something called spherical harmonics, which is the kind of math you study when you're in college. And basically they use these very elegant mathematical equations to get what's called different degrees of the gravitational field that tell you about the layered subsurface structure. And so that's how we think that there's a rocky, so there's a metal core that's high density, and then there's a layer of rock that kind of has a medium density, and then there's a layer of ice that has a lower density. And that's what gives us the densities of those layers and also their approximate thicknesses.
Yeah, math, the real world math. When people ask, when do I need to use this? There it is, finding life in the solar system, right?
Yep.
We talked a little bit about the orbits, and a really good question came in that I've actually never thought about. So why is it that Europa Clipper would orbit Jupiter and not Europa itself?
That's a really good question. And the answer is radiation. So Jupiter has this really strong magnetic field, which means that basically it accelerates what's called charged particles, and that creates a whole bunch of radiation right at Europa. So Io and Europa are both deep within this radiation field that's around Jupiter. And so what that means is that radiation is very bad, right? So if you were a human and you're walking on the surface of Europa, you would have to have like a gigantic lead cube for your spacesuit, or you would just get fried by this radiation and you would just die, right? Even if you brought, a whole spacesuit like on the moon that had air and everything you needed in it, the radiation would not be friendly to astronauts on the surface. And so the same thing goes for robots. Robots don't like radiation either. And so if the Europa Clipper spacecraft was actually in orbit around Europa, we think it could only survive for about a month or two before the computers on the spacecraft stopped working very well. And so that's why we came up with this compromise where instead of orbiting around Europa, we orbit around Jupiter. And so that's where we have these flybys. So we go into where all this radiation is around Europa. We take all of our close approach observations. That's kind of when we're holding our breath, right? And then we get out of there. We go back out of the radiation belt. So further away from Europa, further away from Jupiter, kind of on the parts of Jupiter where the radiation isn't so bad. And that's where we play back all our data. So we try to minimize the amount of time we spend in too close to Europa. And that means that your mission can last for years instead of for just a month or two.
Awesome. Yeah, that makes a lot of sense. Just like Juno does, these very highly elliptical orbits.
Right.
So, I mean, that does kind of spell out a mission timeline then if we were to ever get approved for something like the Europa lander. It would be a pretty short-term mission then.
That's right. And that's one of the one of the things we have to be really careful about when landing on Europa is that if you're on the surface of Europa, then there's nowhere to hide from the radiation. And so that's part of why the mission would basically, it would only probably be able to last like a month or two on the surface before things started to sort of degrade and not work as well. And so on the Europa lander concept, there's what's called a vault. And so basically it's kind of like a big cube of thick metal material that helps shield all of the really sensitive instruments. So the chemical analysis instruments are inside the vault. That was that kind of rectangular or square looking box that was sort of the body of the spacecraft. And so that's why you have an arm that basically goes out, it scoops up some material, and then it brings it inside the spacecraft where all the instruments are kind of hiding in there where they're safe. And you bring the material to them and they can study it inside the vault where they're more protected. But yeah, the mission lifetime is definitely something that we're paying attention to. And one of the ways we get around that is by having a lot of autonomy. So that means that you basically program the spacecraft ahead of time to basically say, okay, land on the surface. And then instead of like on Mars, where you land and then on Mars, you have the luxury of being close by and also just time on the surface. And so, the Perseverance has been on the surface for what, almost 2 months now, and it's only driven like this little tiny bit of a way, and they're trying to get the helicopter going. But on Europa, your whole mission would be over basically by now. If we'd landed in February, Europa lander would basically be done. And so what that means is that rather than letting humans on the ground kind of make all the decisions, you put some good software on the lander and you say, okay, land on the surface, pick a good place, take your first sample and start analyzing it, and then send us back all the data and we'll tell you where to go next. But we basically are going to need to make the spacecraft able to do a lot of this stuff on its own, just because we have such a short amount of time on the surface to do the mission.
Yeah, so I have one last question, and I admit it's the one that I'm always asking myself, and I know so many students have asked me about, which is obviously incredibly exciting with Europa Clipper, even more amazing if we get a Europa lander. But when, if ever, would it be possible to actually go inside? Is it possible to ever be underneath the surfaces, and is that something that we're looking at?
Yeah, that's what we all want. I mean, I want to get in that ocean. Remember that video I showed of the hydrothermal system on Earth at the bottom of Earth's ocean? I want to go into Europa's ocean in a little submarine and look around and see what's there and go down to the bottom. Oh, that's what I want to do. And it's going to happen. It's going to take a while, right? First, we need to go back and study it, and then we're going to need to go and land on the surface and actually see how thick that ice layer really is. One of the advantages of it being ice is that it's actually, you can melt your way down, right? So it's hard. If you remember the InSight mission that was on the surface of Mars, they were trying to kind of go down into the subsurface with the heat probe, and it turned out to be pretty hard to get that thing to go down. One of the advantages of Europa is that if you bring a heat source with you, you can kind of melt your way down through the ice layer. So it might take a while, it might take a year or two, depending on how thick it is. But it certainly is possible to do it. And then you bring a little submarine or something with you, and then once you get all the way down through, you just let your sub go, and it goes and it explores the ocean. I can't wait for that to happen, but it's not going to be anytime soon, unfortunately. We're going to have to be patient.
Yeah, hopefully our young viewers, by the time you work at NASA, this would be the kind of mission you'd be working on.
Absolutely.
And Cynthia and I will be rooting for you. Hopefully,
yep.
Hopefully not still at NASA. Well, thank you so much for your time. I really, really appreciate it. I think there's just so much exciting research to be done in Europa and Enceladus, and to think that there are oceans in space, not in some distant solar system, but in our backyard. Is just, I think, really, really exciting destinations to explore. So with the last few minutes, what I'd love to do is show you guys just a few slides from the education office to kind of show you how it is that you can take these types of lessons and questions to your students. So on my very first slide, you'll see that we have an education webpage filled with activities, all standards aligned, and you can go through this website and use drop-down menus to really get to exactly what grade level you're looking for, the type of topic you're interested in. On slide 2, you'll see an example of one of these for young kids thinking about what water means here on Earth, right? So thinking about weather and climate. This is an activity called precipitation towers that young students can use this to look at how rainfall patterns occur in different cities across the country and across the globe. On slide 3, we have this really cool activity, graphing sea level rise, and also a kind of a follow-up lesson that was actually developed by a teacher who submitted it to us, which we love. We love seeing all the really exciting things you do with your kids on how you get them excited about science. So, and again, same thing here. This is now looking a little bit more of a middle schoolish activity, but how is it that you can look at how sea level has changed on our planet over many, many years, and students can graph that out. On slide 4, you'll see more of a high school geology activity, thinking about exactly as Cynthia was discussing, about what those hydrothermal vents kind of bring with, how are rocks formed there, what type of energy is being released, and what kind of rock structures we might expect on the ocean floor. So this is a really cool one. On slide 5, you'll see that, again, I'm thinking more of an Earth perspective, because there's so much for us to discuss here in addition to these watery worlds in our solar system. So this website here is one of my personal favorites. It's climate.nasa.gov, and it's a great opportunity for you and your students to explore kind of the Earth's pulse. How is it doing? How has global temperature changed over time? What are more current carbon dioxide levels, and how have those changed? And all of this data is available and interactive for you guys. On slide 6, you'll see the website for our news page. So this is a place where you can find some articles that my team and I have put together that will really break down some of these cool new topics in space, whether it is Earth, weather, climate, or Europa. All of these kind of happenings at NASA are written at the level for you and your kids. So this is a really good place to kind of just stay up to in the news on everything that we're doing at JPL and NASA abroad. On slide 7, again, this is just a closer look at the teach portion of the education page. And I wanted to highlight this because we break this down into 2 portions. The teach page is written for you as an educator. Everything's already lesson planned. Student worksheets and assessments and answer keys are already prepared. So this is a place for you, whether you're in person or remote, to kind of have an opportunity to have a lesson kind of created for you to take off the shelf, as opposed to our learn section, which is written a little bit more for students to drive, right? If you see that on slide 8, that section is kind of something that you would give to a student for them to take, and then they would run with that independently. It's written more directed for students with step-by-step and pictures and so forth. On slide 9, you'll see that this is just kind of the icing on the cake as to the website overall. The learning space section of our page is, to kind of assist whether you're homeschooling or teaching from home, what kind of activities and kind of collections that you guys can use as you kind of address different topics in science. And of course, lastly, on slide 10, the Educator Resource Center and Teaching Space section are where you as teachers can find, kind of some access to what it is that we're doing, what activities we have aligned, collections just like the one I shared today, including our educator workshop this Saturday. So if you are a teacher and you want to see some of these activities done, and you want to share some of the activities that you've done with the community, come out and meet with us, and we'll kind of talk through them and model some of them together. So we can just kind of share best practices about how it is that we can take this really exciting topic and put it into our classrooms. So with that, I'll thank you guys so much for your time today. I really appreciate you dialing in. And of course, in the coming months, we'll have other really cool topics like exoplanets and asteroids and comets. So if you enjoyed today, I hope I see you again next month. And until then, thank you so much for everything you do. Have a great day.